Quality education is a human right.
Hey guys, today we're going to review a pre-calculus topic, namely graphing rational functions. The first topic that we're going to highlight is discontinuities. This is a very important topic in pre-calculus, and there are three types of discontinuities. The first one that we're going to talk about is a jump discontinuity. This is when a function, as it approaches a point, jumps on the y-axis, and as you can notice that one of these dots are filled in, meaning that the one that is filled in is an actual value. Because if we had both of them filled in, then they wouldn't pass the vertical line test, meaning that this would not be a function. Our second discontinuity is our whole/removable discontinuity. This is when a function never disconnects, but as we approach a point, there is a removable point or a hole. In this specific example, the hole is x sub 0. Our last one is our asymptotic discontinuity. This is when we have an invisible line where the function can never cross but can approach. But there are two exceptions to this. With a horizontal asymptote, a function can cross once or twice, but the end behavior will never touch the asymptote. And the second example is a slanted asymptote. Again, the function can cross, but cannot end on the asymptote. Now, let's tackle our first rational function. This is our first example of a rational function. It is considered a rational function because it has variables in the numerator and variables in the denominator. And this down here is our characteristics that we are trying to find of this rational function. To first do that, we must factor out the numerator and the denominator. So to do that, we find two numbers that multiply to 6, then add up to 5, and we get x plus 2, x plus 3. Then for the bottom, we try to find two numbers that multiply to 14 and add up to 9, which we get x plus 7 and x plus 2. Now, for our wholes, we will first see which factors cancel out from the numerator and the denominator. And as we can see, we have x plus 2 in the numerator and x plus 2 in the denominator, meaning that our first whole will be x equals -2. Next, for our x-intercepts, our x-intercepts are the factors that are left in the numerator. So we have x plus 3. We have x plus 3. And so our our x-intercept is x equals to -3. Then for our vertical asymptote, our vertical asymptotes are our factors that are left from the bottom. So what we have in the bottom is x plus 7. And so our vertical asymptote will be x equals -7. Now, for y-intercept, we have to plug in 0 into this rational function. Now, we can do it in the factored form, or we could do it in the standard form. And we're going to do it in the standard form because it is easier. So we plug in 0. So 0 squared is just 0, plus 5 times 0 is 0. We're left with 6. 6 in the numerator. Six. And then for the denominator, we plug in 0, x 0 squared is 0, plus 9 times 0 is 0, plus 14. So we have 14 in the bottom, which we can simplify to 3 over 7. Now, before we tackle the horizontal asymptote for this example, let's look at the 3 cases that the horizontal asymptote has. The cases for a horizontal asymptote are determined by the degree in the numerator and the degree in the denominator. Now, let's look at our first case of a horizontal asymptote, which is when P and M are the same. In this case, our horizontal asymptote is our leading coefficient in the numerator over our leading coefficient in the denominator, just like A over B, this example. In our second case, that is when P is less than M. So the degree in the numerator is less than the degree in the denominator, which gives us y equals 0. So our horizontal asymptote is y equals 0. And lastly, for our final case, that is when the degree in the numerator is bigger than the degree in the denominator. And for this case, we're going to have to do long division, which will give us a horizontal asymptote that is slanted. Now let's go back to our example and see which case applies to that rational function. So to find a horizontal asymptote for our example, we need to look at the leading degrees of both numerator and denominator. So we see that in the numerator we have 2, in the denominator we also have 2. So if you remember that this P equals to M is our case 1. This means that our horizontal asymptote is our leading coefficient over our leading coefficient in the numerator over the leading coefficient in the denominator. So our leading coefficient here, we don't have any, but that is just 1. And in the bottom, again, we do not have leading coefficient, but we know that there is a 1 there, so we put 1 again. And so our horizontal asymptote is 1 over 1, or just y equals 1. Now, we are going to use these characteristics to graph this rational function. To graph a rational function, let's first graph our asymptotes. So our vertical asymptote is when x equals 7. So I will draw a dashed line going down on -7. Then our next asymptote is our horizontal asymptote, which is y equals 1. So I will draw a horizontal dashed line on y equals 1. Next, we want to draw is our points. So our x-intercept and our y-intercept. So for our x-intercept is x equals 3. So you will graph, put a point on x equals 3, -3, sorry. And y equals 6 over 14, which is right under 1/2. So we'll put that right there. And now, with our asymptotes and our points, we can determine our end behavior going right. So we know that our graph is going to look like this, plateauing near the asymptote. And then our left side is going to look like this, plateauing near -7. And now we want to determine if we have any, or we have a graph either down here, or up here or down here. So to do that, we are gonna plug in a point, and let's plug in -8 since it's past the asymptote. So f -8 and that is just 5. So this is good because then it tells us that our graph is going to be in quadrant 2 instead of being quadrant 3 down here. So with that, we're going to draw our graph plateauing this way, not crossing the asymptote, and our graph going that way. Now, if it was down here, we would have our graph looking like this. But since our point was -8, 5, our point is going to be up there. Then lastly, we are going to graph our hole, which is at x equals -2. So x equals -2. And that lets us know that we have a hole right there. And let's try this again with another example. So for this example, as we did before, we are going to first factor the numerator and denominator. So we can factor out a 3 in the numerator. So that leaves us 3 times x minus 1. And in the denominator, we see that we can factor an x. So we will do that. So we get x squared minus 7x plus 6. Now that we have a quadratic, we can factor it easily. So first, the numerator stays the same, so 3 times x minus 1 over, we bring over the x, then we try to find something that multiplies to 6 and adds up to 7, and we get x minus 6 times x minus 1. Now we can use this to find our characteristics. The first thing we're going to do is find our holes. So we will cancel what we find in top and bottom, which is x minus 1 and x minus 1, meaning that our hole is x equals to 1. Next are x-intercepts, which is just what we have on the top. But since we have no more variables top anymore, we are just going to say we have none x-intercepts or no x-intercepts. And for our vertical asymptotes, we look at our factors that are in the denominator, which is just x and x minus 6. So our vertical asymptotes are x equals to 0 and x equals to 6. And now for our y-intercept, we just plug in 0 into our rational function. So we get in the numerator 3 times 0 is just 0 minus 3. So y equals to -3. And now we need to plug in the top. And so 0 cubed is just 0 minus 7 times 0 is just 0 again. And then plus 6 times 0 is just 0 again. So we have 0 at the bottom. Now you'll notice that we can't divide by 0. And that just is undefined, or in other words, we don't have a y-intercept. And now, lastly, for our horizontal asymptotes, remember we look at the powers of our numerator, and here, since we have nothing, we know that that is a 1 and a 3. And now pause me and try to figure out what case we are in. That is correct. We are in case 2, which means that our horizontal asymptote is just y equals 0. Now, let's use these characteristics to graph this function. Let's start by graphing the vertical asymptotes, or the asymptotes. So, our first vertical asymptote is when x equals 0. So, drawing a line on x equals 0. And then our next one is when x equals 6. So here we have another dashed line. Remember to make them dashed. And our horizontal asymptote of y equals 0. Now we are going to draw our x-intercepts and y-intercepts, but since we have none, we are going to have to plug in points to find where our function lies. So for the first part, we will plug in a point here to find if the function's here or down here. And so let's plug in -1. And so f of -1 is just 3/7. So we are going to plot our point at -1 at 3/7, which tells us that our point is up here rather than down here. So we're going to draw the end behavior, going close to the asymptote, but not touching it. And down here as well. Okay. Next, we are going to find if if our graph lies here or down here. So let's plug in 2 since 1 is our whole, but we will graph that later. So f of 2 is -3/8. So we will plot that point as -3/8, which is around down here. And this tells me that my graph is on the bottom rather than on top. And our end behavior will look like this and like this. Oh, a bit too close. Don't forget your arrows. And then, again, for our last part, we will plug in another point to check if it's on the bottom or in the top. And let's plug in f of -7/7, which is just 3/7. So let's plug in that point 7, then 3 over 7. And let's finally graph our last section. Going up here and going down here. Now, let's not forget our hole, which is at x equals to 1. So we will draw a hole right here. And now let's look at one more example to see the case 3 of a horizontal asymptote. Now for this example, the first thing we want to do, like we did with the other examples, is factor. And I noticed that in the numerator, I could factor an x. So we get x squared minus 25. Put 2. Then for the bottom, I notice I can factor out -5. So -5x squared plus x minus 6 squared. There. Now we are not done yet because we didn't factor completely. So we bring over our x. Note that the difference of squares. So x minus 5 and x plus 5. Then for the bottom, bring over our -5. And we find two numbers that multiply to -6 and add up to 2x. So we get x minus 2 times x plus 3. And that is our fully factored function. And now the next thing we want to do is find the holes. And I noticed that we don't have any holes. We don't have anything that cancels from both bottom and top. So what we are going to write is that we have no holes or none. Now for our x-intercept, it is what is left on top. And you notice that we have 3, the x minus 5, and x plus 5, meaning that my x-intercepts are x equals -5, 0, and 5. Then for vertical asymptotes, we look at the bottom and see what factors we have missing from there. And so we know we have an x minus 2 and x plus 3, meaning that our vertical asymptotes are x equals 2 and x equals -2. Then for our horizontal our y-intercept, we notice that we just plug in 0 for our numerator and our denominator, which leaves us with y equals 0 in the numerator, and then 0, 5 times 0 is 0, and 5 times 0, -5 times 0 is 0, plus 30. With 30, which means that our y-intercept is just 0. And it is important that we find the denominator after finding the numerator, even if it's 0, because then if we had 0 over 0, we'd have undefined, meaning that we would have none, or no intercept, or y-intercept. And now, lastly, is a horizontal asymptote, which we remember we're looking at case 3, because the power in the exponent in the numerator is bigger than the exponent in the denominator, which means that we will have to use long division. And in the next slide, we are going to review with an example. Here, we're going to review long division. And the first thing I want to mention is that we cannot use synthetic division because we have a degree of 2 in the denominator and a leading coefficient of 2. When in synthetic division, we need a leading coefficient of 1 and a degree of 1. And so, let's rewrite this. And what I want to first highlight is our 2x squared and our 6x to the 4th. And I want to know what number gets me from 2 to 6, which is just 3. And how many x's I need to get me to x4th from x squared, so that's just x squared. And now I'm going to distribute this to my divisor. It leaves me with 6x to the 4th plus 3x cubed plus 3x squared. And before I combine everything, I am going to multiply everything by -1, and so the signs are going to change. We have -6x to the 4th minus 3x cubed minus 3x squared. And now we can combine. So we get 0. And then we get 8x cubed plus 19x squared. Oh, sorry, not 19. 18. X squared. And this is plus. So, and then again, I'm going to focus on my x, or my 8x cubed and my 2x squared, and I want to know what number gets me to 8 from 2, so that is just 4. How many x I need to x squared from x squared to x cubed, which is just 1x. And so then I will do again, I will multiply again, I will distribute the 4x to my divisor, and that is 8x cubed. Oh, I forgot an important step. We must, before we multiply, we must first bring down our 11x. So our next term, which we're going to put plus 11x. Okay, let's go back. So then we multiply. We distribute our 4x to our divisor. So ax cubed, and then 4x squared. That is the plus, and then lastly plus 4x. Again, just like we did before, we are going to multiply by -1, so everything becomes a negative. and then we can combine. That leaves us with, well, x cubed minus x cubed. Ax cubed is just 0. And 18 x squared minus 4x squared is 14 x squared. And 11x minus 4x is 7x. Now, again, we bring down our 9. Plus 9. And we then look again at the 14x squared and our 2x. And what number gets me to 14 to 7? And how many x's I need? Well, I don't need any x's because I already have the required amount. So we do 14x squared plus 7x and plus 7. Lastly, we multiply by -1. So all the signs change. And then we can combine. We can combine. Here we get 0, here we get 0, and we are left with +2. And now our remainder is +2, and how we write that is, up here we do plus since it is a plus. And then 2 over my divisor plus x plus 1. And that is how you do long division. Now, let's apply long division onto our example from before. Now we are going to apply long division to our example to find our slanted slope. And first we are going to rewrite it. And the first thing I want to point out is that we have a 0x squared and a +0. And it's important that we have these so that we could have all of our exponents represented, because in our rational function 4 we have no x squared. But when we're dividing, even with synthetic division, we want to represent all of our exponents. So that is why we put an x squared and a 0. Now, first, like before, we look at our -5x and our x cubed, and we figure out what gets us to 1 from -5, and that is -1 over 5. After that, we want to focus on our x's and how many x's we need. So we are x squared and we need to get x cubed, so we just need 1x. Now we distribute that to our divisor, so it becomes x cubed plus x squared and then minus 6 And then before we combine, we have to multiply by -1. So this becomes negative. This one right here becomes positive. And now we can combine. So x cubed minus x cubed is just 0. And we get negative x squared and then we get 25x, negative 25x plus 6x, which is 19, or negative 19x. Then we bring down our 0. So we have plus 0. Then again, we want to look at our -5 and our -1 here, since we have a -1. And we want to realize we want to know what number gets us to -1 from -5. And that is just plus 1, since we are saying negative. Okay. Then we distribute. So we get negative x squared negative x plus 6. Then before we distribute, combine, add, we need to multiply by -1. So this becomes a positive. This also becomes a positive. And this one becomes negative. And then we can combine. Oh, sorry. Combine. And that leaves us with negative 18x minus 6. And now we can't divide anymore because our degree in our divisor is bigger than our degree in our dividend. So usually we would put the remainder back in the quotient, but since we are trying to find the slanted slope, slanted asymptote, we are gonna leave the remainder and just focus on our quotient up here. So that means that our horizontal asymptote is -1 over 5x plus 1 and that is our horizontal slope, the asymptote, our slanted asymptote. And now we are going to use the characteristics from before and a horizontal asymptote to graph this rational function. So the first thing we want to graph is our asymptotes. So our first vertical asymptote is at x equals -3. So we're going to make a dashed line on x equals -3. Next, we have vertical asymptote at x equals 2. So we are going to draw dashed line on x equals 2. Then for a horizontal asymptote, we are going to graph that like it's a regular line. So we know we have a y-intercept of 1/5, so we're going to put 1/5 right there. Then we're going to use the slope as any other slope using rise over run. But since we are going negative, we're going to go 1 up, then 5 to the left. So 1, 2, 3, 4, 5. And here is our point. Then again, 1, 2, then 1, 1, 2, 3, 4, 5. And that is our point. Now, you just draw our asymptote. And next, we will graph our points. So we have our x-intercepts. First one we have is -5, which is great because then it tells us the end behavior here instead of just having us to graph or plot a point somewhere to figure out where if it's on the top or on the bottom. Next we have 0 and then 5. So again, it's also great because it tells me the end behavior is going to be up here and not down here. So since our y-intercept is y equals 0, we already have that graphed. And we have no holes. So let's just start graphing our function. We know the end behavior is going to be like this, getting close to the asymptote, but not touching it. So it also is going to get close, but not going to touch it. Again here, close, start plateauing. This one as well, start plateauing. Now, for this one, we are going to have to plug in a point because we don't know if our graph is going to look like this or if it's going to look like this. So let's plug in f of 1, which equals -6 over 5. You're going to plot that point down here. So 1 and -6 over 5. So right after 1, right here. And then that tells us the end behavior because then we know that our function is going to have the end behavior going down here, getting close but not touching, and we have to cross through that x-intercept / y-intercept, and I'm gonna go up here. This has been graphing rational functions. Note that discontinuities are a very important topic in calculus, particularly when trying to find limits.
If you have any questions or any practice problems you would like to understand better, please comment them down below. During our bi-weekly Q&A, we will tackle these problems from the comment section.
Please like and subscribe so that our videos can reach more calculus students. See you next time, you sleuths.